All right, AP 5.7, last video in the chapter, enthalpies of formation versus reactions. All right, we got to go through some vocab first. All right, so we got enthalpies, so delta H, formations, okay, little f. So we're going to start with enthalpy of formations first. So we already know standard enthalpy is delta H. The units are kilojoules per mole. The word standard actually means something. It's a set conditions, which means all of the values that you're given, they have to be at a constant pressure, 1 atm, and they have to be at a constant temperature. So when they're talking about standard state of conditions, these values that they give you, so values given, have to be at standard state. Okay, so at that constant pressure, constant temperature, okay? So when we take these two words and put them together, well, we already have the word standard. Standard means 1 atm, 25 degrees Celsius, of enthalpy, delta H, and then formation. What it represents is the change in heat, the change in enthalpy, when you form, when you combined, and produce 1 mole of a compound. So you take the elemental forms, so pure elements, and you combine to make 1 mole of a compound, okay? And that compound can be whatever state of matter. These elements can be whatever state of matter, but this is the key part, the pure elemental form, okay? So now we got to go back to basic chemistry. We got to know what are the states of matter for elements, okay, in its natural state, okay? So what are the states of matters for elements in their natural states? So for example, carbon is a solid, naturally a solid, okay? Oxygen, O2, naturally a gas. H2, naturally a gas. N2, gas. Calcium metal, solid. You have aluminum, solid, okay? What are their natural states of matters? What you find is that all of their standard enthalpy values, we don't even have to look them up. They are all 0. Okay, so all of the standard enthalpy values in their standard state are all 0s. So no values will be given if they're in standard form, pure elemental form, okay? So as you see right here, I took a screenshot of a chart with standard enthalpy values. So notice right here, you see this little degree sign. So that little degree sign, let me fix my little degrees, my little line here. That little degree sign right there, that's what the standard represents. So when you see that little degree sign, that degree sign means 1 atm, 25 degrees Celsius. We already know we have delta H, which enthalpies, delta H, and then we have the word formation, so we put that little F for it. So we're going to be taking elemental forms and making 1 mole of a compound, okay? So notice all of these compounds, gases, liquids, they all got values. There's no point to memorize these. I have no clue what any of these values are by memory. But notice these two. Pure elemental form. 0. AP may give you some love and actually tell you that the values are 0. That's awesome if they do. But you should know that any pure elemental form, the enthalpy values will always be 0. Okay? So, a little note before we practice. Do not confuse bond enthalpy that's coming in chapter 8 with enthalpy of formation. These are two separate things. Just give me a little full warning before we get into chapter 8. Okay? So we have a calculation that we use. Now we're going to be using this chart for the practice problem, so I'm going to come back to it. So in AP Learning Target 3.B, calculate the enthalpy change. So calculate delta H for a chemical or physical process based on the standard enthalpy of formations. The standard enthalpy of formations, these are the chart values. These are the chart values for any element or compound. Okay, now I want to go back to this chart real quick. If by chance this H2 and O2 was something else, like for example, what if it would have said like H2 as a liquid? Okay, well, we can make gases into liquid, we just cool them down. There will be a value for the delta H. And why? Because hydrogen naturally is not a liquid. This is not its pure elemental form. So be very careful of states of matters. Okay, I'm just bringing that up because you're going to see in the practice problems. So how do we calculate it? Well, AP gives us some love, and I know it looks like a mean equation, but it's actually very simple and fun. We take the tables of the standard enthalpy of formation and we can use it to calculate the enthalpy of reaction. So these values right here, how was formation and reaction similar to each other? Well, these values come from the chart. We need the standard enthalpy values. We need the standard enthalpy values of formation to calculate delta H reaction. Okay, so what we do is we take all of the values added up for the products and we subtract it and get all of the values for the reactants. This little Greek symbol, I believe it's called sigma. That's how I learned it back in the day. Sigma just means add up values. So we're going to take all the values for the product, add them up, all the values for the reactant, and then we subtract. So on your equation sheet, AP does give you some love, which you see a delta S value coming soon. This is going to happen in chapter 19. So don't worry, you're just going to do the same thing with some different values. So one warning, because we're going to do a practice problem, pay close attention to coefficients. Okay, so remember when you have those values for coefficients, you have to take the enthalpy values and you have to multiply them by whatever coefficients that they have. Okay, so if you need some love from Fairbra, go to his YouTube video, 6.6 to 6.9, fast forward about 38 minutes, and then you can get some love from him too. Okay, if you want to follow along with me, let's do this together. So enthalpy of formation, let's calculate the delta H reaction for the following, and I'm going to put that little degree sign, it should be there. Use the delta H formation values given above, which we're going to use that chart that was above. Pay close attention to coefficients and phases, as in states of matter. If we do this right, we should get this answer, okay? So I'm going to zoom out some so I can see these values that are over here, okay? So first thing I like to do is I need to locate the values. I need to locate the delta H formation values, okay? And then I just put them under the chemicals first. So methane as a gas, I'm going to find that guy right there. So there he is. So I'm going to put negative 74.8. And notice it says kilojoules per mole. So kilojoules per mole. I only have 1 mole, so that guy's done. Now notice right here, O2, I'm going to go and cross them out. Okay, no value. And why? Because this is its pure elemental form. Do you have to write this on the AP test? No, 0 is just fine. Okay, don't waste our time. CO2 as a gas, so CO2 as a gas right here, and I'm going to put negative 393.5 kilojoules per mole. And now I got to be very careful with water, because I got water on here twice. Water as a gas versus water as a liquid. Well, this balance equation has water as a gas. So I'm going to take this value right there as the gas, but notice it has a coefficient. So I'm going to take 2 times this negative 241.8 kilojoules per mole. Well, let's bust out that calculator. Let's go ahead and plug that in. So we got 2 times negative 241.8. So I'm going to go ahead and just write that number right below it. Okay. Don't worry about rounding or anything, just plug in the numbers. You're more concerned about sig figs. I have one after the decimal. Let's keep the one after decimal going. So now I'm going to add up my reactants, which my reactants was negative 74.8 kilojoules. And my products, we're going to add those two up, add it to that negative 393.5. And I'm going to get negative 877. Oops, get rid of that decimal. 877.1. And we still have one after the decimal, kilojoules per mole. So now I'm going to write my equation. Delta H reaction, okay, standard state. I'm going to say the sum of the delta H values for the products, okay, minus the sum of the delta H formation values of the reactants. Okay? If you want to say capital P and capital R, there's nothing wrong with that. Okay? Products minus reactants. So be very careful. It's not the left number minus the right number. Okay? It's products. Negative 877.1 kilojoules per mole minus a negative number. Okay? So this is when final answer, okay, sig figs, rounding, whatever we need. Well, the cool part is both of them have one after the decimal, okay? So I'm going to plug in that negative 877.1 minus a negative 74.8. Well, obviously when I subtract this negative number, that's going to become positive. But this number is so negative, our answer is going to stay negative. And our answer will be 802.3. And then kilojoules per mole. And that's it. Very exothermic reaction. Very exo, since delta H is negative. Okay? So, practice problem 2. What if I take the same equation, but I take that water as a gas and I change it to liquid, okay? So I'm just going to scroll up and I'm going to write down the same values, okay? So now this delta H right here, we still have the same thing, 74.8. All I'm doing is going to change that into a liquid. Let's see how changing the state of matter changes the delta H. So kilojoules per mole. We know this guy's 0. CO2, negative 393.5 kilojoules per mole. Now for the water as the liquid, I want that value. So I'm going to take negative 285.8. Now, let's talk about that. Liquid versus gas. Gas requires more heat, okay? Liquids require less heat. So you notice this value right here, this is a more negative number versus this is a less negative number. This value right here is higher than the liquid value. So when we take this value, multiply by 2, plug it in, let's see how it changes. Does this value get more negative or does it get less negative? Okay, so I'm going to add these two up. Oh, I got to take my 2 times my negative 285.8. And I get right here negative 571.6. And I'm going to add these two together. 393.5. So I get a total right here at negative 965.1 kilojoules per mole. Okay, compared to over here, if I look up to the gas, negative 877. This definitely right here, that is a higher value since it's a gas. Water is a gas. Compared to this value is lower, even more exothermic, since water is a liquid. AP can even ask you a question like this without even calculating anything. How is this liquid going to change the delta H value? Is it going to be more negative, less negative, or the same? Well, obviously it's not the same. So delta H reaction, standard state. I'm going to take my sum of my delta H values, little formation, you could do capital P, and then the sum of the delta H formation of the reactants. So my products was negative 965.1 kilojoules per mole. And I'm going to subtract it by that negative 74.8. Okay, so I have that number minus a negative 74.8. And if you predict it correctly, this number should be more negative. Negative 890.3 kilojoules per mole. Okay, so it is more negative since water was a liquid versus gas. Okay, so if I would have had water as a solid, it would get even more negative. Okay, because solids require even less heat. Okay, so last practice problem, AP style. Okay, a student measures the enthalpy of combustion of propene. Propene is right here. And vinyl chloride. The student determines the combustion of 2.00 mole of vinyl chloride releases 2,300 kilojoules. And actually, I labeled that wrong. That one's not propene. I was just noticing that. This one right here, this is vinyl chloride. So you're probably asking yourself, well, where's this propene? Okay. It says it releases 2,300 kilojoules of energy, as you see in the equation below. So right there, negative 2,300. So this balance equation with these chemicals and these coefficients, it has a delta H. From this right here, all they did was take products minus reactants, and they got this value. All right. So now, what if you change the equation? Using the table of standard enthalpies of formation. So remember, they got to give you the values if they want you to calculate. So these right here, these are all of the delta H standard state formation values. Determine whether the combustion, well, what's combustion mean? Reacts with O2. And as you see right there, I'm reacting with O2 of 2 moles of propene. There's my propene. You don't even have to know who the heck propene is, as in like what is he in life, stuff like that. That 2 moles is because of that right there, because of his coefficient. Okay. Will it release more, less, or the same energy as 2 moles of vinyl chloride? Well, notice that 2 moles of vinyl chloride because it has a coefficient of 2. Will this number be more, less, or the same energy as that negative 2,300? Okay, justify, which means you can use any evidence you want, and I would be using math. Okay, your balance equation is below. Okay, so your C3H6 right there, your oxygen, well, they were nice to you again. Okay, and then you got your 6 CO2. There he is right there as a gas. And then I got my water as a gas also. Okay. Show your work below. Don't forget to multiply by the coefficients, products minus reactants. If you do this right, you should get 3858, which means this reaction right here is even less energy than this one. Okay. See you on the next one.